This is a video from section 3.4 in linear algebra. Find vector and parametric equations of the line containing the point and parallel to the vector. In number 1, the point is -4, 1. The vector is 0, -8. The vector equation can be written as follows. xy is equal to the position vector of the point plus a scalar multiple of the vector parallel to the given line. So in other words, xy is equal to -4, 1 plus t times 0, 8. To get the parametric equations, we just equate components. So notice x is equal to -4 plus 0t, right? And then y is equal to 1 plus 8t. And those are the parametric equations. Number 2, suppose we're given the point 2, -1 and the vector -4, -2. The vector equation is xy is equal to 2, -1, that's the position vector of the point, plus t times -4, -2. So again, -4, -2 is the vector parallel to the line we want. Now, the parametric equations. So I'm going to take x and set it equal to 2 minus 4t. And then y is equal to -1 minus 2t. And those are the parametric equations. In number 3, suppose the point is 0, 0, 0, and the vector is -3, 0, 1. So same idea, just in 3 space. The vector equation is xyz is equal to 0, 0, 0, the position vector of the point, plus t times -3, 0, 1. Now, to get the parametric equations, I'm going to take x and set it equal to -3t. And then y, you can say y equals 0. I just said y equals 0t. And then z equals 1t. So I just equated components to get the parametric equations. Number 4, suppose we have the point -9, 3, 4, and the vector v, which is -1, 6, 0. The vector equation is xyz is -9, 3, 4, that's the position vector of the point, plus t times -1, 6, 0. -1, 6, 0 is the vector that runs parallel to the line we want. The parametric equations for this line, I'm going to take x and set it equal to -9 minus t. Y is equal to 3 plus 6t. Z is equal to 4 plus 0t. Again, totally fine if you just want to write z equals 4. But that would be the parametric equations for number 4. Okay. The directions. Use the given equation of a line to find a point on the line and a vector parallel to the line. So basically, we want to work backwards from the first 4. And with that, let's take a look at number 5. Now, x equals 3 minus 5t, and then negative 6 minus t. So that's the vector. But we can write this as 3 negative 6 plus negative 5t negative t. But this is equal to 3 negative 6 plus t times the vector negative 5 negative 1. So you notice how I'm working backwards the whole time. So the point on the line I would argue that it's going to be 3 negative 6. And then a vector parallel to the line. That will be negative 5, negative 1. So just kind of a game of working backwards. Let's take a look at 6. Suppose x, y, z is equal to 4t, 7, 4 plus 3t. Okay. Now, I'm going to do this too, all right? I'm going to write this as 0 plus 4t, 7 plus 0t, 4 plus 3t. So I want every component basically to have a number, a term that has a number and a term that has some scalar multiple of t. Because watch what happens. I'm going to take this and write it as 0, 7, 4 plus 4t, 0t, 3t, right? And this can be written as 0, 7, 4 plus t times 4, 0, 3. And so I would, again, argue the point here is 0, 7, 4. And then that's the point on the line. So let's actually say that. So the point on the line is going to be 0, 7, 4. And then a vector parallel to the line that's going to be 4, 0, 3. And that's how we do 6. Number 7. X equals 1 minus t times 4, 6 plus t times negative 2, 0. Okay? Now, essentially what I'm going to do is combine these and then break it apart. So in other words, I'm going to write this as 1 minus t times 4, 1 minus t times 6, plus negative 2t, 0. Okay? Now, we can go further than that. Now, we can write this as 4 minus 4t, 6 minus 6t, plus negative 2t, 0. And so this is 4 minus 6t, right? Because I'm going to take 4 minus 4t and add negative 2t. That's where I'm getting the 4 minus 6t from. And then we get 6 minus 6t. But this is 4, 6, the vector 4, 6 plus the vector negative 6t, negative 6t. And so this is 4, 6 plus t times negative 6, negative 6. So a point on the line I would argue that we can use 4, 6. A vector parallel to the given line I can use negative 6, negative 6. Now, here's a question, though. Does the vector 1, 1 work? So that's kind of a food for thought. Okay? Now, here's some directions. Find vector and parametric equations of the plane that contains the given point and is parallel to the two vectors. Okay, this is good for us. These types of questions are a little different than what you would get in like a traditional Calc 3. So if I give you the point, negative 3, 1, 0, and then V1 is equal to 0, negative 3, 6, and V2 is equal to negative 5, 1, 2. So I'm going to go, let's do the vector equation first. So I'm going to go x, y, z is equal to the point. That's in fact, the position vector of the point, plus t1 times 0, negative 3, 6, plus t2 times negative 5, 1, 2. And you're done. So what are the parametric equations? Well, just like with lines, I'm going to equate components. So x is equal to negative 3 minus 5t2. Y equals 1 minus 3t1 plus 1t2. And then z is equal to 0 plus 6t1 plus 2t2. That's it. And so it's just another way to represent the equation of a plane. and quite different than what you would get in a Calculus 3, which is why it's pretty good to go over. So if we take a look at 11, all right, on 11, we have the point -1, 1, 4. And the vectors v1 is equal to the vector 6, -1, 0, and v2 is the vector -1, 3, 1. So let's look at the vector equation. So I'm going to take x, y, z, and I'm going to take the position vector of the point, which is -1, 1, 4, plus t sub 1 times 6, -1, 0, plus t sub 2 times -1, 3, 1. Now, what are the parametric equations? Now, let's take a look at that. So x is -1 plus 6t1 minus 1t2. Y is 1 minus 1t1 plus 3t2. And z is 4 plus 0t1 plus 1t2. Again, totally fine if you want to say z is equal to 4 plus t2. That completely works. The directions. So the question says, find the general solution to the linear system and confirm that the row vectors of the coefficient matrix are orthogonal to the solution vectors. Are orthogonal to the solution vectors. Phenomenal question. Okay. And with that, we're going to take a look at 17. Suppose I told you x1 plus x2 plus x3 equals 0. 2x1 plus 2x2 plus 2x3 equals 0. And then 3x1 plus 3x2 plus 3x3 equals 0. Okay? It's actually not as bad as it looks. So we're going to set up our augmented matrix. So we get 1, 1, 1, 0, 2, 2, 2, 0, 3, 3, 3, 0. Okay? Now, I'm going to take -2 row 1, add it to row 2, put the result back into row 2. I'm going to take negative 3, row 1, add it to row 3, put the result back into row 3. And when that occurs, we get 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? Okay, so what does that mean? x1 plus x2 plus x3 equals 0. And we have, basically we have two free variables. I'm going to let x2 equal r and x3 equal s. So x1 is negative r minus s. Okay? Now, x1, x2, x3 is equal to negative r minus s, r, s. Right? That's the solution to the system, or the general solution. Now, we could also write this as negative r, r, 0 plus negative s, 0, s, right? Now, this is r times negative 1, 1, 0 plus s times negative 1, 0, 1. And I want you to notice something. So if I take the row vector of each row vector of the coefficient matrix. So if I take 1, 1, 1, and I'm going to dot it with negative 1, 1, 0. Notice how I get negative 1 plus 1 plus 0. That's 0. If I take 1, 1, 1 and dot it with negative 1, 0, 1, do you agree that that's negative 1 plus 0 plus 1, which is also 0? And I would argue that if we go to 2, 2, 2 and 3, 3, 3, we're going to get the same thing. So if I take 2, 2, 2 and dot it with negative 1, 1, 0, right? And I get negative 2 plus 2 plus 0, which is 0. And then 2, 2, 2, dotted with negative 1, 0, 1, which is negative 2 plus 0 plus 2, which is 0. And then last set, 3, 3, 3, dotted with negative 1, 1, 0 is 0. And then 3, 3, 3, dotted with negative 1, 0, 1 is also 0. So notice how V1 is negative 1, 1, 0, right? And V2 is negative 1, 0, 1. And then any linear combination of these two vectors just so happens to be a solution to that system as well. Any linear combination. So that was what I wanted to comment on for problem number 17. And that'll do it for this video for section 3.4. We did problems 1, 2, 3, 4, 5, 6, 7, 9, 11, and then 17. Thank you.